All right, open up your book to section 10-2, page 496 in your book. Title of this section is Cartesian Equations for Conic Sections. The objective is given a Cartesian equation for a conic section, transform it to other equivalent forms, and then sketch or plot the graph. And secondly, given the graph of a conic section, write a Cartesian equation. Let's begin by refreshing our memory here a little bit about completing the square. Kind of alluded to this idea here at the end of the previous video there, indicating that we would want to be able to take that polynomial form of a Cartesian equation, or the polynomial form of the Cartesian equation of a conic, and we wanted to be able to rewrite that back in one of the vertex forms or center radius forms. So in order to do that, we have to do what's called completing the square. So let's refresh our memory here. We talked about this back in chapter 4 when we were dealing with the polynomial and irrational functions. So we have seen this, so hopefully it's just a quick refresher here for us. So if you have the quadratic expression x squared plus bx plus c, we're going to assume that the leading coefficient here, the a, is equal to 1. If it's not, then factor that out from all three terms. So you have it in the form of just x squared plus the other terms. So the first thing you want to do is associate your x squared and your x terms there together. So I'm going to put those in parentheses, x squared plus bx plus c. The next thing you do, here's the magic you got to remember, which is how do I find the number that makes this a perfect square? And you find that by taking half of the x coefficient and squaring it. So in this case, our x coefficient is the b. Half of that would be b divided by 2. And then squaring it, of course, gives us the b squared over 4. That's the number we need to know to make this a perfect square. Half of the middle term, or half of the x term there, and square it. You then have to do what's called adding a clever form of 0. We've talked about multiplying by clever forms of 0 many times. Adding a clever form of 0 just means that you take z and you subtract z, and you get 0, of course, when you do that. So we're going to add in z somewhere, and then we're going to subtract out z. The net result is, of course, that we've added 0. That's a clever form of 0. So this value that we calculated up in the previous step there, that b squared over 4, I've got to add that in. I'm going to add that in associated with the x squared and the x term there. So it's x squared plus bx plus b squared over 4. Of course, when I add that in, I've changed the expression, so I better subtract it back out. That's my clever form of 0. So with the c term, I'm subtracting out the b squared over 4. And now the first part of this is a perfect square. So now we can actually factor that quadratic, and we can write it as x plus b over 2 quantity squared. That right there is a perfect square. And now, of course, you've got this other constant there at the end there. If we had that x squared plus bx plus c, it is now equal to this guy right here. It's equivalent form, but I've got it written in a perfect square form. That we need to be able to do in order to answer some questions here, and in particular to go from the polynomial form back to that center radius form or that vertex form for a parabola. All right, take a look at example 7 here on page 504. It says transform the equation 9x squared minus 4y squared plus 90x minus 32y plus 197 equals 0 to the center radius form by completing the square. This is what we were just talking about. Let's write down this equation here. 9x squared minus 4y squared plus 90x minus 32y plus the 197 is equal to 0. All right, so we got ourselves the polynomial form. So before we get to completing the square, let's first get our terms together here. I need to get my x's together and my y's together. So I've got a 9x squared. I've got a plus 90x. So I'm going to put those two guys together. I'll put them in parentheses. Let's get our y terms together here. So it's plus, I've got a negative 4y squared and a minus 32y. And the constant there, I'm actually going to end up moving that to the other side. I think I'm going to go ahead and do that in the same step. Just subtract the 197. If you wanted to do that in a separate step, you certainly could do that, but that constant 197 needs to be moved over to the other side. All right. We're going to end up completing the square for each of these things that have got in parentheses. I got to do it twice here. But for completing the square, I want to have the coefficient in front of the x squared or the y squared as being 1. So let's factor out the coefficients that are there right now. So I've got a 9. I got to factor that out and write this as x squared plus 10x when I factor out the 9. Here we're going to factor out a negative 4, so it's going to be a minus 4 times y squared plus 8y. That's equal to the negative 197. All right, so far we just kind of played around with the equation right now. We've just done some algebra on it. Now comes the completing the square part. I need to make each one of these a perfect square. This guy right here needs to turn into a perfect square, and this guy right here needs to turn into a perfect square. All right, so I got to do the completing the square twice here. All right, I've got 9 times x squared plus 10x, and now I need to know what constant do I have to add to this to make this a perfect square. There's only one constant that will work. And the way you find that is you take half of this x term here, the coefficient, which is 10. Half of 10 is 5, and square it, which would be 25. That's the magic number I need there to make that a perfect square. Any other value plugged in there for that constant, it's not a perfect square. With 25, it is. We're going to do the same thing over here for the y terms there. So I've got y squared plus the 8y, and again, I need to know what's the number I need to add here to make this a perfect square. So take the coefficient of the y term there, that's the 8. Take half of that, which is 4, and square it. We end up with 16. Now for this I'm going to, well, let me first write the negative 197. For this I'm going to, instead of adding a clever form of 1, like we talked about on the previous slide there, instead what we're going to do, since we have an equation, I just want to balance the equation. So whatever I did over on the left side, I'm going to do the same thing on the right side in terms of this constant that got added in. The key here to remember with this is that I didn't just add a 25. I added 9 times 25 on the left side. So that means that I have to add that same thing over on the right side. 9 times 25 is better known as 225. So I added 9 times 25 on the left side. I now added the same thing, 225 over on the right side. Same thing here with the 16. Again, I did not add just 16 over on the right side. It was actually a negative 4 times 16. Actually, I didn't even add it. I subtracted, right? So I've got to do the same thing over on the right side. 4 times 16, that's 64. So I've got to subtract off 64 over on the right side. So we're just balancing the equation, just the same way you work with any other equation. The same reason I was able to move the 197 over to the right side. I subtracted 197 from both sides to make that happen. Here I'm adding 2 numbers on the left side. I got to add the same 2 numbers over on the right side. All right, let's write this as a perfect square now. Leave your 9 out front, and then x squared plus 10x plus 5, or sorry, plus 25 becomes x plus 5 squared. And then it's y squared plus 8y plus 16, that's y plus 4 quantity squared. And then let's simplify this, the value that we've got over there on the other side there. Negative 197 and 225, that sounds like 228. And you're subtracting 64 from that, which sounds like a negative 36 is what we should end up with. Grab your calculator and punch that in to make sure you got the right value there, but that's what we should end up with, I think, in this case. And now let's divide by the negative 136. Remember that the center radius form has this set equal to 1, so that's why I'm going to divide everything by a negative 36. So we've got 9 over x plus 5 squared divided by a negative 36. Divide that first term by the negative 36. Do the same thing for the second term. We've got a negative 4 times y plus 4 over the negative 36 is equal to 1 now. We divided everything by negative 36. All right, when we divide it by the negative 36 now, I'll actually simplify here. 9 over 36, that'll give me the same as 1 over 4 when I simplify that. So, and it's negative now, right? It's a negative x plus 5 squared divided by 4. And this one here, because it's a negative over negative, this one becomes positive now for the y's. 4 over 36, that's better known as 1 over 9. So I'm going to write that as y plus 4 squared divided by 9 is equal to 1. And we're really close to the form we want, but I actually want to write this whole term here as just one thing squared. And this is one thing squared. So I've got to think about rewriting that denominator as being a perfect square as well. And those actually are pretty easy to do. I'm going to go ahead and write it in 2 steps here just so you can see what we're doing, but obviously you can do it in 1 step here. 4 is the same as 2 squared. And the 9 is better known as, or is also known as 3 squared. And now I can write this as its center radius form, which is x plus 5 divided by the 2 quantity squared. That's what we want to do. Do the same thing for the y's here. It's y plus 4 divided by 3 squared is equal to 1. And it looks like we end up with a hyperbola then, right? Because the signs here are opposite. That tells me that this is a hyperbola. We could talk about all the details of this hyperbola now, where the center is at, what your x dilation, y dilation are to help us sketching this thing. There's lots of things we can do with this equation now. Many times this is a more helpful equation if we're trying to come up with a sketch, or if I'm given a sketch, write it out. I want to see it written in this form. Let's go back to the original and just note a couple of things here. Notice on the original that the sign of the 9 here, I'll put a plus out in front. That's a plus 9, and this is a minus 4. Those are opposite signs. When they're opposite, that's a hint that this is a hyperbola. Okay, but if I asked you at this point, what's the center of this hyperbola, what's the x dilation, what's the y dilation, we wouldn't know those numbers. This is the reason why going through these steps to get it into this form is very helpful. Now I know exactly where the center's at. I know the direction it opens up in. I know what the x dilation, y dilation are. I could actually sketch this thing. All right. Here is our polynomial form for a conic, written as a Cartesian equation in the polynomial form. Ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. Now we just went through the steps there to be able to rewrite this in its center radius form, and that would help me be able to graph that particular conic. It turns out that I can take this equation and manipulate it to get an equation for what y is equal to as a function of x. So let's see if we can do that. So since I already have this set equal to 0, what I really have here, if I think about solving this for y using the quadratic formula, what I really have here is a quadratic equation written in terms of y. But probably it would be helpful if we rewrite it so it looks more like that. So normally if we have a quadratic equation, we put the y squared term first, or whatever the squared term is. So let's take this cy squared and write that first. I'll do it in black here. Cy squared. And then we write our y term second. So we've got our cy squared already taken care of. Then we write our y term second. Now this has a y in it, and this has a y in it. So let's factor out the y from each of those and write it next. So I've got a bxy and an ey. So if I factor out the y, I'd have bx plus e, and that's multiplied by y. So I've got something times y squared plus something times y. And then the last part is then the constant, which the constant is whatever doesn't have a y in it. So I've got an ax squared, which I know sounds weird to call that a constant when there's an x in there, but in terms of y, there's no y's in it, so therefore that would be a constant term for y. So it's the ax squared, you've got a dx, and you've got f. This is equal to 0. This right here is a quadratic equation. I've got something squared, something times y squared plus something times y plus something that doesn't have y's in it is equal to 0. We have a quadratic formula that tells us how to solve these equations. If you want to solve this for y, our quadratic formula tells us the following. Y is equal to, it's the opposite of the middle term here. So it's the opposite of bx plus e plus or minus the square root of, the square root part's going to be pretty big here, plus or minus the square root of the middle term squared here. So it's the bx plus e squared minus 4 times the first term, which is c, times the last term, which is the ax squared plus dx plus f. And that all is divided by 2 times the leading coefficient, 2 times c in this case. I just took that equation, that polynomial form, and I solved it for y using the quadratic formula. Now realize I get 2 solutions here. There's a plus or a minus. In the case of sketching an ellipse, for example, you see the top half of it and the bottom half of it. In the case of sketching a hyperbola, you're going to see the same thing. There's a top half and a bottom half to that it's going to sketch. But we end up with an equation then that represents the equation solved for y as a function of x. I could now take this equation, plug it into my y equals menu, and I could graph this. This is another way for me to graph that conic then without having to go through all the steps there to actually find the center radius form, like we just saw in the previous example. It would be nice, though, if it would just automatically dump this equation. That's a pretty long equation to type in. If it would just dump that equation right into y1 for me, or I guess probably y1 and y2, since I have 2 equations here that I've got to deal with. So I've given you a program that's going to do that. And so let's try using that program. That's what the next example is about. Take a look at example 8, page 505. It says, use your graphing program to plot this equation here, 9x squared. Let me go ahead and write this down. 9x squared. I'm going to go ahead and write plus 0xy. I didn't write that down, but that way when I go to plug in values, I'll remember to plug that in correctly there. Plus 25y squared minus 36x minus 200y plus 211. And that is equal to 0. Which that sounds a lot like the equation that we were dealing with the other day when we were converting that conic into its polynomial form. We had an ellipse, so we converted over to its polynomial form. We got this. So they want us to sketch this. All right. Assume that you're just given this equation. Can you graph this? Well, again, we could go through the steps we just went through and write this in as a function of x. Solve for y as a function of x using your quadratic formula. But even better yet, we can grab our calculator and do this. So let's run our program here on our calculator. Grab your calculator. All right, so with your calculator here, let's run our little conic program that you have. So starts out by showing you the formula that we're using, ax squared plus bxy plus cy squared plus dx plus ey plus f. So that's the entire equation there set equal to 0. And that's going to ask us for our values of a through f here. So again, a is 9. There's no xy term, so that's 0. C is 25. D was a negative 36. E was equal to a negative 200y. And the f value was the 211. All right, if we just press enter there, it should go ahead and graph this for us. It does a pretty decent job of sketching this, although it looks like it's an ellipse that's been broken open at the ends. Just realize that's your calculator having trouble sketching this properly for you. It should actually close there on the ends, but our calculator wasn't quite able to handle that. But that's a pretty decent sketch of this. It doesn't show me, it doesn't tell me exactly what the center and the x and y radius are, but or dilation factors are, but I could probably approximate those from this graph. So this alone probably doesn't tell me as much as that center radius form does, but it is a quick way for me to come up with what the sketch of that conic would be. From the equation, we can tell it's an ellipse. Let me grab a picture of this. Again, from the original equation they gave us here, we should have been able to tell that it was the ellipse, and that's because you've got both your x squared term and your y squared term are both the same sign. They're both positive. That's the key. This here is positive, and this is positive. And since they're different values, that tells me that it's not the circle. All right, if they were both 9 or both 25, I'd end up with a circle. They're different values here, so that means that I'm going to end up with the ellipse. All right. So before we even started, we probably should have started with that actually and just said, what kind of conic is it? I guess I recognized that that was the equation we were working with the other day, so I knew it was the ellipse. But that's really the first part is, what kind of conic is it, and then can we sketch it? So there we go. We've got ourselves a nice little program that will sketch this thing for us. And just so you understand what the program is doing, if you go to your y equals menu, you'll notice that all it did was take those two equations we came up with. It was a plus or a minus, so I say it's two equations. One's with a plus in it, and one's with a minus in it. If you look there, there's a plus right here in front of this square root in equation 1 in y1, and it's got a minus there in equation number 2 in front of that square root. So it's just taken that equation, dumped it into y1 and y2, and it's stored the values a, b, c, d, e, and f for you, and boom, it graphs it. The nice thing about this then is if you wanted to just change one of the two numbers there, you could just store that on your home screen, and you could regraph this. You know, if you said, oops, A was supposed to be 16, not 9, or something like that, you could just simply say 16 stored at alpha A, and you're all ready to graph again. Okay, it's going to graph that for you with that new value of A plugged in there. So that is the program there. All right, that right there is the end of the third part here of section 10-2 for us.